Okay, let's get going. By the way, I couldn't help but notice last class there seemed to be enough to notice anyway, several instances of people just getting up and walking out, coming back, and it happens like, once or so during the class period, that's one thing, but it was a number of people happening all class long, and it's okay, it's annoying to have it happen that much. I mean, yes, things happen, but if you can wait till after class, please do. Okay. Okay. When I got here today, there were no markers in the room, and I really thought I had packed some in my bag, but no. And so I went upstairs to Dean's office, and it gave me this one and said, "Oh, it's new." And I can tell already from the little I've written, it's not. So we'll see how this goes. Okay. So from last time, I was talking about general first order linear equations. Just first order, not necessarily linear. Linear will be Monday's topic. Now, if I go ahead and write it this way, f of ty minus f of ty plus dy dt is equal to 0. And then we can multiply this equation by whatever we want. Of some function mu yet to be determined, but one that is designed to make it easier for us to solve the equation. And this function is called an integrating factor. And this is compared to df dt plus df dy. dy dt is equal to 0, where f, big F, when set equal to 0, describes the solution of the ODE, and therefore this mysterious function big F has to satisfy mu. Okay. All right. Now, I won't repeat here, but it was done last time. It boiled down to trying to make sure that this equation was satisfied. Minus mu yf minus mu fy is equal to mu t. Okay. Now, that's for any first order equation. Now we're going to focus on one particular type of first order equation where things become a lot simpler. So this ODE is said to be separable if it is possible to write f of ty as some function of t, which we'll call g of t, times some function of y, h of y. So if it is possible in any way to break it down like that, then it's separable. So some examples. like t squared times y, that would give you a separable dE. Whereas if I just change this a little bit, t squared plus y, that is not separable. That actually falls in the category of linear equations. Actually, this first one, that would give you an equation that is both linear and separable. Those are easier still. So generally, when you have f of ty being a sum of things, it's unlikely, although not outside of a possibility, that's going to be separable. When you have a product of things, that's what you're looking for, to see if it's separable or not. Okay. So, under this assumption that it is separable, what can we do with all this to find a solution? What it allows us to do is make a simplifying assumption about this mysterious integrating factor, mu. Okay. Because before, mu is allowed to be a function of both t and y. We're not going to do that anymore with separable. That is a function of y only, not t. So therefore, derivative of mu with respect to t is 0. So what happens in that case is, if I go back to the equation involving mu and f over there, I can rearrange. I set the right side to 0, and I can rearrange. So mu prime over mu is equal to minus h prime over h. Well, okay. Someone's going to ask me, where did I get that? So I'm just going to work out the whole thing. So I'll fill in what f is. F is equal to g times h. Okay. Minus mu times g times h, derivative with respect to y, and that is equal to 0. Now, if I take a derivative of all this with respect to y, really it's going to be differentiating only h, because g is a function of only t. So when I'm differentiating with respect to y, g is considered a constant factor. So I can say minus mu y g h is equal to mu g dh dy. Okay. And now I have g in both terms. I can divide both sides by g and cancel it out. So, okay. So that's how I wind up with mu prime over mu is equal to minus h prime over h. So now I have a simpler equation for mu that I can actually try to solve if I can just find the next page. Yes. Okay. Now everything here, mu, h, functions of y. So I can integrate both sides. Okay. With respect to y. And anytime you have the integral of a derivative over a function itself, the long way to do it would be a substitution. I can make a substitution, for example, u is equal to mu. So then du is mu prime dy. So then I'd have du over u. But the integral of that is natural log. So we have natural log of mu is equal to minus natural log of h plus a constant. So one point I want to make here is, anytime you see an integral like this, don't go through the whole, okay, make a do substitution and make it simpler and figure out what it is. You can, it's best if you can recognize this, like, oh, this is just the log of mu, and jump to that directly. Save yourself time. Okay, now, using the properties of logs, I can take this minus sign here and move it up there as an exponent. So what I end up with is also, c can be anything. C is an arbitrary constant. So what I'll do is, I can set it to whatever I feel like, because there's not a unique solution to this. I can just choose the most convenient solution. So if I take the exponential of both sides, I'll have mu of y on the left, and then on the right I'll have h to the minus 1, but that's just 1 over h. So that is my magical integrating factor that makes it possible to solve the equation. So if I go back to the original problem, so minus f of ty plus dy dt is equal to 0. Now, I'll go ahead and write out what f is. So that's g of t h of y. Then I'm going to scale it by my integrating factor. That's 1 over h, which has the effect of canceling out the h. So I have minus g of t plus 1 over h of y, dy dt is equal to 0. Okay. Now the thing is, now that it's in this form, we can actually go ahead and integrate both sides. But I'm going to change notation a little bit just to make things cleaner the rest of the way. This part here, minus g, I'm going to call that capital M of t. This right here, 1 over h of y, I'm going to call capital N of y. So now we have M of t plus N of y dy dt is equal to 0. So any separable equation you're given, like for a homework problem or a test, you're not going to go through all this. I'm just showing where the solution comes from. But what I do recommend you do is write it in this form right away. And you can always algebraically rearrange it to get it there. And this sets you up to actually write down at least a formula from a solution, at least an implicit solution. Because now what you can do is integrate both sides. With respect to t. Now I just went straight to breaking up into two separate integrals, just because the two are going to be treated a little differently. Because now I can make a substitution. If I let u equal y, then du is dy dt dt. So I could think of it like this. Two integrals, one with respect to t, one with respect to y. So now what you can do is just go ahead and work out those integrals, and you'll have some equation involving both t and y that at least implicitly describes the solution. So if I were to number like your steps that you would follow, first get it in that form. Second, integrate n with respect to t, n with respect to y. And as I mentioned at the outset that we're looking for this, f of ty equals 0 implicitly describes the solution. I can now say so big F of ty, which we now know what that is. So it's the integral of n with respect to t plus n with respect to y is equal to 0. So this is this general solution formula. Now, if there's no initial condition, you'll just work out these two integrals, and there'll be an arbitrary constant. And I mentioned before, when you have more than one indefinite integral in an equation, it's only necessary to put a plus c in front of one of them. And that will be used to sort out what the, if you are given initial condition, the initial condition will determine what that constant is. Okay. And that's what we're going to see in some examples here. Okay. And the pages are literally all over the place. Okay. I should mention that the reason why I went through all stuff with the integrating factor is we're going to return to that when we see other types of equations go through a similar process, but we make different assumptions depending on what kind of equation it is. But what we'll see is there's always a solution formula like this. Once you have this, you can try, if possible, if an explicit solution is required, this gives you an equation and you can try to solve for y. Okay. So from a first example, this is an equation that is both separable and linear, just because the y part is just y by itself. Sorry, just making sure the recording is still going. All right. So what I can do is, if I identify what is, so this is my t part. So your m of t is always equal to minus the t part. N of y is always 1 over the y part. So you can just write this down immediately, or I can just rearrange this and write it as minus a of t plus 1 over y dy dt is equal to 0. And you see there's your capital M, there's your capital N. So now we can just jump directly to the solution formula. So what we have is, all right, so minus a of t, whatever it is, plus 1 over y dy is equal to 0. Now, this we can't really do anything with because A of t is not given. I'm doing this example because this is a kind of equation that comes up fairly often. In fact, we've seen it once already in the example I did with the solution in a tank, where we made the assumption that the flow rates in and out were not equal. The one I messed up. And this is just going to be natural log the absolute value of y plus c is equal to 0. So now so this, assuming you've worked out the integral for a of t, whatever a of t you're given, this is an implicit solution. If no explicit solution is required, then you could stop there. But in this case, it is possible to get an explicit solution. Okay. Actually, what I'm going to do, because c can be anything, I'm going to put the c on the right side. And I'm going to move the integral of a there also. Okay. So then I can exponentiate both sides. So my solution formula is explicit solution is e to the integral of a of t dt. And because of, I'll put a constant here. I like to call it c, but I already have a c there, so I'm going to call this c tilde, where c tilde is e to this c. So this right here is an explicit solution. So, hypothetically speaking, if I were to, say, give a problem on a test where I give you an equation that is both separable and linear, like this one right here, so I've specified some particular a of t, then, if you studied well enough, you may remember that you can just jump directly to this and write down the solution. Don't go through all this rearrangement and so forth. That is your solution. And then you would work out that integral. And you're done. And you can just take your points and move on. Hint, hint. So. Whereas other separable equations, for maybe more work involved, because here y is only involved in this in a very simple way. But when the dy dt is a more complicated function of t and y, then there's really more work involved in getting an explicit solution.
So wait, for the sake of it not looking as weird on paper, can we put like the c with the tilde before the e? Or is it actually
Multiplication is commutative. You can put it wherever you want. Actually, I prefer to put it over on the left anyway. Because often, what you could do is c, this constant c tilde here, would really be the initial value, y of 0. And then this would be an integral from 0 to t. So that way it would automatically satisfy the initial condition. But I'm going to talk more about initial value problems in just a little bit. I want to do another example that's more concrete. Well, actually, it'll be using this solution formula right here. Any other questions about this one now? There's one difference in the way I tend to present these things compared to, any textbook on this subject that I've seen, is, they tend to describe how to solve these equations in terms of kind of like a recipe, step by step, do this, do this, do this. And I also do that. But what I also like to do is, when it's possible, is actually give formula. Here's a formula for a solution. Now, you may have a difficult time remembering those, and that's why I show you more of a way to do it. But if you're trusted you have a good memory and you can know those solution formulas, off the top of your head, then it gives you an advantage. Up to you. So we have the next example. Okay. So y prime is equal to 3t squared y. So if you have a separable equation where the y part is just y, not a function of y, just plain old y, then based on the previous example, you can jump directly to this. Y of t is equal to some constant c, because I've not given initial condition here, e to the integral of 3t squared dt. So you go ahead and work out the integral, and that is what? Integral of 3t squared. Yeah, t cubed. And that's it. And if you were also given initial condition, then you could, since we're not really throwing in a plus c, for this integral, we don't really need to because we have an arbitrary constant out here. So if I were to plug in t equals 0, I'd have e to the 0, which is 1. Therefore, the constant in this case is actually y of 0. So if you were given y of 0 as an initial condition, whatever that initial value is, you can just fill in there. So anything like that that is both separable and linear, due to the y part being just y, you can just...
Why is 3t squared again when it's 3t cubed?
Because I messed up. Like I said, you got to keep an eye on me. Thank you for pointing that out. Remember about 10 years ago, one of my students said that math professor tends to say A, mean B, and write C. And I was like, oh, no, I don't do that. Well, she was right. Okay, are we good now? Okay. Any questions about this one? Now, unfortunately, not all separable equations work out as quickly as that, just because the y part would not just be just y. So there's another example like that, where this ODE is already written in the form to use the solution formula. Okay. All right. So this part right here is your capital M of t. This is your capital N of y. So the implicit solution is integral of m of t dt plus integral of n of y dy is equal to 0. So now we just fill in all the pieces. So I have integral of t squared dt plus integral of 1 over y squared dy is equal to 0. So now we can go ahead and evaluate these integrals. Although, because it's t squared dt, I realize it's going to make some of you groan, but I don't care. There's a popular math limerick, and I hope I don't mess that up. So, but it begins, the integral of t squared dt from 1 to the cube root of 3 when times the cosine of 3 pi over 9 is the log of the cube root of e. Okay. And if I did not misremember it, it actually is correct. Cube root of 3 times. Oh. And sure enough, I did not write down what I said. I said cube root of 3. I wrote square root of 3. 3 times cosine 3 pi over 9 is the log of cube. Okay. Yes, that is correct. So the integral of t squared dt from 1 to the cube root of 3, 1 times the cosine of 3 pi over 9 is a log of the cube root of e. Okay. Now, for these integrals that we have here, so we have t cubed over 3 from this one. And here we have y to the minus 2. So the integral of that is minus 1 over y. And we throw in a constant of integration. So now we have, at least without any integrals, and that is something I would expect, like on a test, whatever integrals are involved in your solution formula, those should be worked out. If only an implicit solution is needed, you could stop there. But in this case, once again, it is possible to solve for y, isolate y, and get a explicit solution. And no, I'm not going to throw something on a test like, the integral of e to the minus t squared or something like that, because that was literally proved to be impossible. I don't expect you to remember all of your calculus. Okay. I do, on my test, I do put certain solution formulas, yes.
When do you know you can just jump like straight to the integral of mt dt, integral of ny dy?
Okay.
So you can do that.
When anytime the equation is separable.
Separable?
Yeah, because if you're given something like this, y prime equals whatever, and this is a function of t times a function of y, so that is separable, it is always possible to algebraically rearrange it to get something like this. So, in other words, okay, so y prime is that equal to, so if it's given to you like this, it is always possible to rearrange it like this. And only if it's separable. So, in some cases, and I've seen this like in the homework problems in WebAssign, it's already given to you in this form. On the other hand, if you're given in this form, y prime equals whatever, first check, is it really separable? Otherwise, this won't work. Sorry.
By separable, you say like t is not reliant on y and y is not reliant on t.
Yeah, but you can break it up. Well, it's literally this. You can break it up into a product like that. Yeah. You can separate the time derivative into a product of something of t times something of y. So one of the examples I gave earlier, I had something like this was equal to t squared plus y. Can't separate it. So a different approach would be used for that. And this is something I'll talk more about when it gets closer to test time. The very first thing you want to do when tasked with solving a first order ODE is classify it. Is it separable? Is it linear? Is it exact, etc.? And these classifications will have more meaning as we go through those sections. Because each classification leads to a different solution approach. So this is the first one we're looking at, and there will be more. Okay. And while on the subject of how these equations are written, so we've seen two already. Y prime is some function of t times some function of y. And then this one, m of t plus n of y dy dt is 0. That's another. And yet another that's very similar to this one, but I point it out anyway because you'll see it in WebAssign. What they do is actually multiply both sides by dt. M of t dt plus n of y dy is equal to 0, which then you just put an integral sign in front of it, and then you're on your way to getting your solution. So I'm just pointing this out. You'll see this in the homework, just so you're not thrown off by it. And it seems kind of odd to take something like dt, which this isn't literally thought of as a fraction, because it's a limit. Derivative is defined as a limit of a fraction. So some mathematicians would probably object to treating these as like a numerator and denominator, because that's not technically true. But to take dt as something you can multiply by and write it like this, since you're going to integrate the whole thing, it works. The way these two relate is that m is equal to minus g, n is 1 over h of y. So this could be something you decide to remember. It's interesting that you think of both m and n as like not literally negations, but taking an inverse. Here you're taking an additive inverse of g and a multiplicative inverse of h. Okay. All right. Now, this example is not entirely finished yet. So I have t cubed over 3 minus 1 over y plus equals 0. So now what I can do is I want to get y all by itself. So first I'll get 1 over y by itself. So I have t cubed over 3 plus c is equal to 1 over y. And then I can just take a reciprocal of both sides. So y of t, my explicit solution, is 1 over t cubed over 3 plus a constant. So if you were given an initial condition, that's where you would apply it. So like you would fill in the y value on this side, you'd fill in your initial time right here, and so the only unknown left would be c. The only variable left, so then you can solve for c. So questions about this example? Now, for remaining examples, we'll focus on initial value problems where we have a separable ODE. So what you can do is from your original equation that's written in this form, and here's an initial condition that goes with it. So I'm still going to proceed as before, where I'm going to integrate both sides. But now, because I have the initial condition, I'm going to do it as a definite integral. So I'll have the integral from t naught to capital T because here I'm integrating with respect to lowercase t, so I need to have something different out here for my limit of integration, thus I'm using capital T out there. Now, like before, I can break this up into two integrals. And then in the second one, if I make a substitution, u is equal to y of t, du is y prime of t dt, then this is equal to du. But this is something that might not have been covered or may have been forgotten from Cal 2. If you have a definite integral like this one, and you make a substitution, you got to change the limits. So these limits, t non-capital T, you plug into the substitution to get the new limits. So whereas your original limits were t values, your new limits will be y values. So in the left integral, we have this still. And then here I have y naught, so your initial value down here, and then y of capital T up here. So now, when you have an initial condition, here's how you could proceed. You could just use the solution formula I had before, where it's indefinite integrals, and then you have a plus c to contend with. Or you can do it like this, where your initial time and your initial value are the lower limits of integration. Your independent variable is the upper limit in the first integral. Your solution, this literally what you're trying to solve for, is your upper limit of integration. So then you can work out these integrals, substitute in these limits. There is no plus c because it's a definite integral now. And then you're done. You have your solution. And if an explicit solution is required, you would solve for y of capital T by algebraically rearranging. So if you prefer having solution formulas, this is a one for an initial value problem, as opposed to when I just give you an O to E by itself without any initial condition. Okay. All right. So I'm going to use this now on an equation that actually came up last time. And for that, we were looking at equilibrium solutions and the phase line and all that. But now the goal is to actually solve it. Okay, so the equation for this example is called a logistic equation. So dy dt is equal to some constant r, and then 1 minus y over capital K times y. And the constants r and k are assumed to be positive. And last time we'll discuss was this equation has two equilibrium solutions. Y equals 0 and y equals k. And it was found then that y equals 0 was an unstable equilibrium, and solutions went away from it. Y equals k is a stable equilibrium solution. Okay. Now, here, the right-hand side doesn't depend on t at all. It depends only on y. So, now remember from last time, this is an example of what is called an autonomous equation. An autonomous equation is a time derivative depends only on y, not t. So autonomous equations are always separable because the t part is just 1, or a constant. So what I'm going to do here is, I won't go through all the algebra in this case, but I can, if I want to write it in the same form as I have previously, I can write it like that. Okay. So now, this is my m, that is my n. So my integral function I integrate with respect to t, function I integrate with respect to y. So now I can apply my solution formula that I have over there. So my initial condition y of 0 is equal to some given value y naught. So now, the solution to my initial value problem satisfies this. Integral from 0 to capital T of r dt plus integral from y naught to y of capital T, k over y minus k dy is equal to 0. So so now I have a solution formula for the solution of my initial value problem that already takes the initial condition into account. Okay. Now, let's see how well you remember your Cal 2. Well, first, the original integral on the left, is really easy because r is just a constant. So we're just going to get r times capital T. Now, the way you might be thinking of working this out is, the integral of this is r times t, and then I have limits 0 and capital T, and then you go ahead and plug in these limits, and this is what you get. So here's another shortcut that I often use. If you're integrating a constant and it's a definite integral, the integral is always whatever the constant is times the difference in the limits. So again, save yourself time, jump directly to that. Okay. Now, first integral is easy. This one is not. So again, see how well you remember your Cal 2. For an integral like this, what is the technique that needs to be used to work out something like that? So you don't remember what that's called, or if they don't know the name.
Is it a quotient rule?
What?
Is it a quotient rule?
I'm sorry.
Quotient rule?
That's for differentiation. And unfortunately, the quotient rule has no clear counterpart.
Integration by parts?
That would not help in this case. That would help for some other ones.
Partial fractions?
Partial fractions, yes. Let's see. Now, I won't go through the whole partial fraction decomposition thing in this case, so I'll show you what it breaks down into. So partial fractions are 1 over y minus k minus 1 over y. Okay. Oh, that should be, sorry, my limits are wrong. It should be y naught and y of capital T, like before. Okay. So this fraction, k over y times y minus k, is equal to this. So partial fraction decomposition would give you that. Now, each of these terms can be integrated. So we have R capital T plus natural log of y minus k minus natural log of y with limits y naught and y of capital T is equal to 0. So now you just go about plugging in the limits. It's going to get a little messy here, messier. So we have first upper limit, y of t, which is what we're solving for. We want to try to isolate that if we can. And then minus the values of the lower limits. Don't forget to distribute the minus. Okay, so now all the limits are plugged in. Next, what I want to do is, so if I just go ahead and move the RT to the other side, and I can also use properties of logs. What properties can I use to condense this? I have 4 logarithms there. What properties can I use to condense that into a logarithm of just one entity? Who remembers their properties of logs? What?
You can multiply and divide.
Yeah, so when
Natural log by
the difference of logs is the log of a quotient. The sum of logs is the log of a product. So these properties right here. So ln A plus ln B is ln AB. ln A minus ln B is ln A over B. So I can take the RT, move it to the other side. Anything with a plus in front of it, numerator. Anything with a minus in front of it, denominator. So I have ln of y naught times y of capital T minus k over y of capital T y naught minus k. Equal minus RT, let's make sure it agrees with what's in my notes. Okay, yep. What can I do now with this equation? I want to get rid of the log.
E.
Yeah, take the exponential of both sides. So that will cancel out the log on the left, and then I'll have e to the minus RT on the right. Okay, so now I'll have y naught, y of capital T minus k over y capital T, k is equal to e to the minus RT. Okay. All right. And certainly I can do some rearranging. With the ultimate goal in mind of solving for y of capital T explicitly. Okay. Now, at this point, the absolute values complicate matters because we don't know if what's in the absolute value sign is going to be positive or negative. So I'm going to make an assumption here that will help us. So first I'm going to assume that the initial value is between 0 and k. And in fact, in real applications, it tend to be the assumption that's made about when using a logistic equation, that the initial value is between the two equilibrium values. And And we've already seen from, it can be seen from a direction field, that if the initial value starts between 0 and k, the solution will also be between 0 and k, because we have equilibrium solutions at 0 and k. A solution that starts in between cannot cross them, because if it ever hit that value, it would just stay there. So what's nice about that is k is greater than y of t or y naught. So this is positive, y is positive, and this difference, y naught minus k, is positive. Everything is positive. So now I can drop the absolute values. Okay, so after dropping the absolute values, what I can do is rearrange this so that all terms t in any way are on one side, all other terms on the other side, so that way I can factor out y of t. The result of all that algebra turns out to be this: y naught k up top, and then y naught plus e to the minus r capital T k minus y naught. So this is the explicit solution to the logistic equation.
Wouldn't where it has yt minus k and y0 minus k, wouldn't it be negative since y0 and yt are both less than k? Is something less than when they go towards.
Hold on. Oh. Results still correct, but yes. If,
Because it's in absolute value, so it doesn't truly matter. But
well, as long as they're the same sign, doesn't matter.
right.
That's the key. So yeah, okay. So because both sides are negative, then what I could do is drop the absolute value and then negate, and then then I can proceed like that.
Yeah.
Sorry about that. If whatever expressions were here were different signs, the only way we could drop the absolute value is to negate one of them. Sorry about that. Okay. Now, as far as seeing how the solution behaves, like if you plug in t equals 0, then this exponential becomes 1. The y naughts cancel out, and you have y naught times k over k. The k's cancel, and you're left with y naught. So it satisfies the initial condition. But what's more interesting is, what happens as t goes to infinity? So, as t goes to infinity, because r is a positive constant, so what happens to e to the minus rt as t goes to infinity? How does an exponential like that behave? Anyone? Something? Yes.
Would it go to 0?
Yes. So very important to know when you have these decaying exponentials, the exponent is going to be negative, as actually goes to 0 very quickly, becomes small quickly. So this part goes to 0. So then, once you get rid of that and see what's left, what do you get from a solution? Yeah, because this part goes away. You have y naught times k over y naught. The y naughts cancel, and you get k. So, and this is in keeping with what was seen yesterday, that y equals k is a stable equilibrium point. So if I start, the solution initial value is between 0 and k, it's not going to go towards 0, that equilibrium, because that's unstable. It's going to go towards a stable equilibrium, k. So you start here, it's going to behave something like that, converging to that line. Okay. Questions about that one? I have a couple more examples, and I think there'll be enough time. All right, so next one we have t e to the t plus times dt. So it's written in this form now, plus y dy is equal to 0. So now what you can do is, okay, initial condition, y0 is equal to 1. So I can integrate from 0 to capital T, t e to the t. 0 comes from the initial time. In my other integral, I have y dy. What are the limits? So y of capital. And then the initial value is the lower limit. That's equal to 0. So this describes the solution of my initial value problem. Now, if I were to evaluate this integral, what technique would I have to use for that? Yeah, integration by parts. And what you end up getting for that is t minus 1 e to the t with limits. So this would be the u, and this would be the dv when you're using the integration by parts formula. So anytime you have a polynomial times an exponential, set u equal to the polynomial, because the degree decreases, at some point it goes away. And only because of time, I'm not working through the integral in this part. I will mention, though, when it comes time for tests, I do provide formula sheets for the tests. So there's certain formulas, things I would not expect you to memorize would be on it, but you still got to be able to use them in the time given. So when a practice test is put out, the formula sheet will be included, so you will know what things you don't have to try to commit to memory. Okay, so that's this integral after carrying integration by parts. And then here we have y squared over 2 with limits 1 and y of t is equal to 0. So now what you can do is just go ahead and, should be capital T here, go ahead and plug in the limits in both. So then I have y of t squared over 2 minus 1/2 is equal to 0. So that's just from plugging in the limits. And once you simplify everything as much as you can, okay, so I have t minus 1, e to the t, minus 1 times e to the 0, which is 1. So now I have
Just one.
minus 1 minus, wait,
It's just one.
Um,
Negatives cancel.
yeah, that's right here in my notes. Okay, I need the class to end. Yeah, so minus 1 e to the 0 minus gives you plus 1. Plus 1 minus 1/2 gives you a, so if I could get rid of this now, and then as a plus 1/2. Okay. Okay. And actually, what I'll do then is multiply everything by 2, and I want to isolate y of t. So y of t squared is going to be equal to 2 times 1 minus t e to the t, from negating the t minus 1 by moving it to the other side, minus 1. So now I can take the square root of both sides, and that is my solution. Now, can anyone tell me why I need the positive square root? Or how would I know that it should be a positive square root?
Because your intervals are from 0 on up, and you wouldn't have anything.
Well, it's initial conditions.
Oh.
So if I plug in t equals 0, I need this to be 1. So that's... And remember, these kind of initial value problems have a unique solution. If you get a situation where y of t squared is equal to something, and take square root, there has to be one correct choice, and the initial condition leads you to that. All right. Yes, I hear you getting restless, but I do have 5 minutes. While my hearing has gone bad over the years, I am still attuned to the sound of packing up. So I have y prime is 2t over y plus y is equal to minus 2. Here, it's not obvious right away that it's separable, but I can factor the y out in the denominator, and that's how we can see that it is. So if I were to rearrange this to be in the same form as usual, I'd have 2t over 1 plus t squared minus y dy dt is equal to 0. So if I go ahead and set up the integrals, my initial time is 0, and I have 2t over 1 plus t squared dt minus the lower limit is minus 2, because that's the initial value to y of t, y dy. So what happens in this case is you go ahead and evaluate the integrals. The integral of this is natural log of 1 plus t squared with limits 0 and t, and all this is equal to 0. So this is equal to, if I just move this to the other side, y of t squared over 2 with limits minus 2, just y squared over 2 with limits minus 2 and y of t. So then you go ahead and plug in both the limits. Now, when I plug in the lower limit of 0, I get natural log of 1, which is what? What is the natural log of 1? 0. So that's one of those good to remember things. So only the upper limit will make a contribution. Natural log of 1 plus capital T squared. And then I'll have y of capital T squared over 2 minus 2 squared over 2. So now I can isolate y of t squared at least, and I get, if I multiply through by 2 and move that to the other side, then I get 2 natural log 1 plus t squared plus 4. And then I take the square root but this initial value problem, and these have a unique solution. So when it comes to plus or minus square root, There can be only one. So
Negative.
yes, so you plug in t equals 0 here, and you get plus or minus square root of 4, so plus or minus 2. Not done yet. Everybody's so anxious to start the next class. Why? Okay, and that's it for that one. Again, make sure you use your initial condition to determine which square root, if that comes up, in solving for y of t. Okay, so good luck with the homework on this. That'll be due on Monday. Yes.
Where did the 2t in the numerator of the MOT go?
What happens here to work out this integral? You do a substitution. U is 1 plus t squared.
Okay.
Yeah.
I see.
So as the examples today show, you're not listening anymore anyway. Okay. Know your integration techniques.